Hi, Marina.
Hi.
How are you doing tonight?
Yeah. Good. And you?
Good. So you're into piecewise and absolute value functions.
Yes.
Okay. Well, let's graph this first. How do we graph a piecewise function? Piecewise usually means that it's not continuous. In other words, you'd have to lift up the pencil in order to graph it.
Well, we just learned about it, so I don't
Okay.
remember really.
Well, what it says here is that we basically have two different functions. We have y equals x minus 4 whenever x is greater than 0. And we have y equal minus x plus 1 whenever x is less than or equal to 0. So to the right of the axis, I'm basically looking at this function, y equal x minus 4. As long as I am to the right of the y-axis, that's what the function is. So how do I graph y equal x minus 4? What's the y?
4 to the right.
What's the y-intercept? In other words, if we look at all functions as being y equal mx plus b, we know that b is the y-intercept and the slope is m. So in this particular function, what is b?
4.
Negative 4. Because notice that it's plus b. So if I'm looking at a minus 4, then I know the y-intercept has to be negative 4. What's the slope of this function? What is m?
1.
Okay, good. Positive 1, which means I go up 1 and over 1. So if that is 4 on the x-axis, then I'm going to have a slope of about 90 degrees. And this is actually an open dot, not a closed dot. Yeah, I erased the... Hold on, I'll put it back. So it's open dot because this is whenever x is greater than 0, not counting equal to 0. And then the second function, in other words, this is this function here. The second part of the piecewise function is y equals negative x plus 1 whenever we are to the left of the y-axis, or whenever x is negative, or equal to 0. So how would I plot y equals minus x plus 1? Where would its y-intercept be?
For the first equation?
No, we're talking about the one over here now. How would I plot that? The trick here is to plot each of them separately.
It'd be positive 1.
Okay, so I know that it goes through there, and this time it is a closed dot because it's whenever x is less than or equal to 0. And what is the slope on this function?
1. I mean negative 1.
Negative 1. And negative 1 is the same angle as positive 1, but it goes like this. In other words, this has negative slope. The one on the right has positive slope. So now we've graphed it entirely. And that's exactly how to do these piecewise functions, is you start to the right of the y-axis because x is greater than 0, so I'm going to plot the line x minus 4. And then to the left of the y-axis, when x is less than or equal to 0, I'm going to plot the line y equal minus x plus 1. And the net result that I have is this function here. Now, it wants the domain and range of this function. And this, incidentally, goes all the way. What's the domain of the function?
Which one?
The entire, in other words, the entire function is actually y. It's equal to a combination of two functions, but they want the domain of this entire piecewise function. So if you look at the graph, what's the domain look like? What can x be?
All real numbers?
Good.
Or, but yeah.
That's correct. X can be from negative infinity up to 0. X can be 0, and then x can be any value to the right of 0.
My teacher, she taught us like it would be 0 is, well, not for this problem, but just for an example, it would be like 0 is greater than x, but x is greater than 0.
Okay. When we get to that kind of a problem, why don't you bring that up again? Because I'm not sure what you mean.
Okay.
What's the range of this? Again, looking at the graph. So when we're defining range, we're going to define it by y. Y has to be what?
Greater than 4? Or equal?
Greater than negative 4. This is negative 4 down here. And not equal. It can't be equal to negative 4, but it can certainly be greater than 4. If you follow the y-axis and take that to infinity, then y can be any number greater than negative 4. It could be negative 3 right there. It could be negative 2. It can be 0. We don't even need this part on the left. In other words, that entire range came from just the right side of this function. Okay. Let's go to the next one. So remember, the secret here is to merely graph it in pieces. But you have to know how to graph the pieces. Okay, so here, when, let me put negative 1 on there. Y is equal to minus 2x plus 5 whenever x is less than or equal to minus 1. So since it's less than or equal to minus 1, I'm going to go over here and I'm going to start my graph and I'm going to go left to take care of this part of the piecewise function. Now, where am I going to start?
The y-intercept 5.
Correct. The y-intercept is 5. Hold on a second. Let me think about this for a second. So the y-intercept being 5, 1, 2, 3, 4, 5 would be up here. And what's the slope?
-2.
Okay, good. So normally I would draw that kind of like this. It would be steep. Okay, that's a slope of -2. And normally I would come all the way to there to graph that equation. However, it's only equal to that equation when x is less than or equal to -1. So I actually have to go back to about this point, no, actually all the way up to here, and erase that part of it, because it's not equal to that when x is greater than 1. It's only equal to that line when x is less than or equal to -1. You see where I'm, here, let me redo my axis here a little bit. I don't really have it in the right spot. Let's call this point, I don't need to label 0, you know where 0 is. Let's label this point right here -1 on the x-axis. Okay, so you see how I'm plotting this function?
No, I don't get it.
Okay, let me go down a little bit here. How would you plot y equal -2x plus 5? You would go to the y-intercept, which is 5.
Yeah.
And then you would draw a straight line through that with a slope of -2. So that's how we would plot it. But the thing is that our piecewise function says that it's only equal to this when x is less than or equal to -1. Well, here's where x is -1, which means this function is not that to the right of -1. It's got to stop right there. So that's how I would plot that if I said x has to be less than or equal to -1. I would only draw the first part of the function. Okay? So,
how do you know which angle it goes up to?
well, I guess that this has a slope of -2. I didn't count it out, but it means that we go down 2 over 1, down 2 over 1. It's not important really to draw it so accurately as to see how these piecewise functions work. So let's look at the second part of that function. The second part says that whenever x is greater than -1, that the function is not the same anymore. Now it's still a straight line, but it's this straight line. Okay, so first of all, let's plot that without this condition. How would I plot y equals 3x minus 2? How do you start?
The y-intercept is -2.
Okay, so that goes through that point right there. What's the slope?
3.
Positive 3, which is a steeper slope than this one. So I'm just going to approximate that slope here, and I'm going to draw it like this. Only I can't go to the left of -1 because this says that it's only equal to this function when x is greater than -1. So I'm going to erase, and I'm only going to draw this. There's the slope of 3. but I'm only going to take it to -1 right there with an open circle, because it's only when it's greater than -1, not greater than or equal to. So there's our combined graph. That's what this piecewise function, how it graphs. In other words, this part is -2x plus 5. This part here is 3x minus 2. And they are exactly as they would be, only this function only goes to where x is -1, and this function only starts at x equal -1, and then goes left, because it's equal to this function whenever x is left of -1. So looking at the graph, what is the domain? And these do go infinitely far in this direction.
Wait, or number 3, is that what you're doing, or number 2?
Number 2, what's the domain on number 2?
Oh,
That's what I've graphed here, is number 2.
Greater than or equal to -1.
Domain is whatever x can be.
It needs to be greater than -1.
No. In other words, there's values of x over here. And in fact, if I carry this forward far enough, I can go all the way to -infinity. So the domain is all reals. Just kind of start out assuming that your domain is all reals unless you can see a place on the graph where it cannot be. In other words, you cannot find a value of x that is can't be put on this graph. I mean, I can't show it because of the scale here, but the domain is from -infinity to +infinity. What's the range? Now, first of all, what is this point? This point right here was -2, where we had a y-intercept.
Y is greater than -2?
Well, look at that graph. Does that look correct?
Greater than or equal to?
Well, it's greater than whatever this value is here. In other words, we don't know at the moment what that value is right there, but that's y goes all the way down to that in the graph. Y starts here and goes up. So y has to be greater than whatever this number is here. How can we find out what the y value is there? Because we didn't plot that when we graphed it. If I look at the second part of the function, this line here, which is 3x minus 2, what is that equal to when x is -1?
-1x.
When I plug in -1 for x, which is what this is right here, then I have 3 times -1 minus 2, that's equal to -5. So this y value that it actually gets down to is -5, only it never quite gets there. It's always greater than that. So I can say that the range, y has to be greater than -5. Can you see that from the graph, why it's -5 and not -2?
Yeah.
Okay.
Yeah.
Right, because -2 is up here, but y actually goes all the way down to this value here with an open circle. and that value is minus 5, and I got it by plugging in x equal minus 1 into this equation right here.
So would it be y is greater than or equal to negative 5?
Just greater than. That's an open circle. In other words, since x, when x is actually equal to minus 1, we revert to this line there. But when x is just barely to the right of negative 1, then y is barely above minus 5. So there's no way for y to ever actually get to be minus 5. However, it goes down and approaches that with the open circle. So that's why we use the greater than sign and not greater than or equal to. All right. Does this represent a function? And explain our reasoning. Well, first of all, let's graph it. We're going to start with the top function. Y equals x plus 4 whenever x is positive or 0. So how do I graph that?
The y-intercept is 4.
Okay. What's the slope?
1.
Okay. So it's a positive slope, so that line goes like that. Now, notice that I started it at 0, and it's a closed dot because x is greater than or equal to 0. This line does not go left of this dot. It goes to the right to infinity. But to the left of this dot, we're actually going to be represented by a different function. And in fact, this function starts at x equals 2, which is right there. So for this function, or part of the function, I want to graph this. How would I graph y equals minus 3x plus 2?
The y-intercept is positive 2.
Okay, so I'm going to put a dot there.
And the slope is negative 3.
Negative 3 is a steep slope, and it's negative. So it's got to go through there, and I'm going to take it all the way to there with a closed dot, because my restriction on this is whenever x is less than or equal to 2, I'm going to use this line with the negative slope. So there's our resultant graph. Now the question is does that represent a function, and why or why not? Is this a function?
Yes.
There's a test for a function called the vertical line test. If I run a vertical line through any part of this, and I find two values of y, which I did here, then it is not a function. Let me draw some examples. Let's talk about functions and not functions. That's a function. because no matter where I draw my vertical line, I only have one value for y. Even if I draw it right there, I only have one value for y. There's a circle, but a circle is not a function. No matter where I draw my vertical line there, I pass through two values for y. So for something to be a function, it has to pass the vertical line test. And that's the easiest way to remember it. Okay, let's look at 4. Okay. First of all, we can see that this piecewise function does one thing when x is negative or 0, and it does something completely else when x is positive. So let's start with the negative part. What is the equation that I can write? Y equals what when x is less than or equal to 0? What is y equal to when you look at that graph?
Number 4.
Yeah. Here, I've got it covered up a little bit here. Here we go.
Like, you want me to tell you equation?
I want you to tell me how to write that as a function. That horizontal line right there. A horizontal line is y equals whatever it is, that number. So the function is y equals 3 whenever x is less than or equal to 0. Well, now let's look at this part of the function. How could I define that? In other words, y equals something else when x is greater than 0, and not greater than or equal to, just greater than, because it's got a dot there. So on this part, what is the y-intercept? Remember, y is equal to mx plus b. So we need to solve for m, and we need to solve for b. Well, we can pull b directly off of the graph, and we can pull m off of the graph also. So what is this part of the function? What's the slope?
3.
Now, what's the slope of this line right here? How many up do you have to go and over? It's the rise over run. Okay, so the slope is 1. So my equation is y equals x, and then what is b? What's the y-intercept of that part?
Oh, -2. So it'd be
Right.
x minus 2.
Yes, exactly. So here's our piecewise function. And whenever x is greater than 0, the function is x minus 2. But whenever x is less than or equal to 0, y is just equal to 3. There's not even an x in there. Because when you have horizontal or vertical lines, horizontal lines are y equals some number. Vertical lines are x equals some number. Now, does this, looking at that graph, does it pass the vertical line test?
Yeah.
Yes, it does. Even if I put my vertical line right over the y-axis, I only have one value for y, and that's 3, because of that closed dot and this open dot. I don't have both of these values when x is equal to 0. I only have this one here. When x is any number greater than 0, then all of a sudden I jump way down here and I continue it on. But, okay, so let's write the function for number 5. What's the first situation that we have to consider? X what? Let's go from left to right, always.
Wait, for which line
For number 5?
Yeah.
So whenever x is what, it's going to be one function. What's the delineation point here?
0.
Okay. So since we're going to handle the function on the left first, let's say x is less than. Is it less than or equal to?
Less than and equal to?
Correct, because we're dealing with this part for the moment. Now let's define that function right there. What's the y-intercept of that function?
4.
What's the slope? Approximately.
Like 1.5?
Well, it looks to me like it goes down 2 over 1. So I would say that's a -2 slope.
Oh.
So there's the equation of the left part of this thing, that part only. Now the right part is going to be whenever x is greater than or equal.
Just greater than?
Good. And now let's define this function. First of all, what's its intercept?
0.
Okay, so I'll put a +0 there just as a marker. What is its slope?
Positive 3.
Good. So what's my equation?
3x plus 0, or just x?
Just 3x. I'll take the way of the 0. So now we've got the answer. This is exactly what they wanted. Y is equal to this function when x is less than or equal to 0, and it's equal to this function when x is greater than 0.
Okay.
So these are actually pretty simple. It's just two functions in one. All right, let's look at, okay, we're going to graph these functions and we're going to compare it to a parent function. The parent function being y equals absolute value of x. And then they want us to describe the domain and range. Well, first of all, let's graph the parent function. Y equals absolute value of x is a big old V. The slope of this part of it is +1. Slope of this part of it is -1. And that function is y equal absolute value of x. So, what would you think y equal absolute value of x plus 2 be? What is this, when they add a number to the end of the function, what is it?
It moves horizontally?
No.
Vertically?
Yep. When it's on the end, it's a vertical shift. So to plot this function, well, they don't really say graph it, but we will. In other words, I just take the parent function and I move it up 2 units. Now, what's the domain of my new function? What can x be?
All numbers above.
No, don't get domain and range confused. Always do domain first and range second. And domain is always what the x can do. Range is always what the y can do. So what possible values can x take on here? Marina?
Can you hear me?
Yes, I can hear you now.
Okay.
So what possible values can x take on my dotted line?
For range or domain?
Domain. Domain is always the x values.
Oh, all real numbers?
Good. How about range?
Y is greater than 2?
Greater than or greater than or equal to?
Equal to?
Exactly right. Okay, so let's erase that one and do the next one. Whoops. Okay, number 7. Here we've got two things happening. We got a -1 being added after the function, and we have a -5 taking place inside the function. So first of all, what's the -1 do?
It goes down vertically 1.
Good. What does the -5 do? Remembering that x minus h is the standard. So what is h here?
-5.
No. If x minus h is the standard, h has to be a +5. +5 means we move to the right 5 units. So to graph this translation, I'm going to go down 1 and right 5. So there's my new vertex right there. So this thing graphs now like this. What's the domain?
All real numbers.
What's the range?
Hold on. Y is greater than or equal to -1.
Good. Oops. I should use the other way around. I should use dotted for my parent because they're hard to erase. Okay, now let's look at one last translation, which is y equals 2 times the absolute value of x. So here I have a number that's in front of my function. What's the consequences of numbers that are in front of the function? It's not a shift, it's called a stretch.
You froze. I didn't hear what you said.
What's that? When you have a number in front of the function, like we do on number 8, then the consequences of this 2 is what?
It moves horizontally.
Well, it's not a horizontal because we do that when it's inside the function. And it's not a vertical shift because it's not +2. When it's a coefficient in front of the function, it is a vertical stretch. That's what it's called, is a vertical stretch. And a vertical stretch looks like this. It makes this thing skinnier by a factor of 2. And notice why. Because every point that would have been on the original function, say I have a point right there, where x is equal to 1, y is equal to 1, Well, now, when x is equal to 1, y is going to be 2. So it's going to be right there. Same thing when I go over to this point here. If x is 3 and y is 3, well, under this function, when x is 3, y is 6. So that's why it gets skinnier, is because every y value is twice as high as it was in the parent function. What's the domain?
All real numbers.
And what's the range?
Y is greater than or equal to 0.
Correct. Okay. Write an equation for the given translation of this parent function. So I'm going to leave that there. Let's call that y equal square root of x, or absolute value of x. Although they don't want us to graph it, they want the reverse of what we did in 6, 7, and 8. They're telling us what the translation is, and they want to know what the function is. So if I go 6 units to the right, what must my function be?
Y equals value.
Absolute value.
Absolute value. X minus 5.
6 units to the right.
Oh, x minus 6.
And it's both, that's inside the absolute value sign, like that.
Yeah.
In other words, if I were to write it this way, that 6 would be a vertical shift down. You see why?
Mm-hmm.
So we have to write it that way there. Okay, number 10, what is a function that would be shifted 3 units up?
It'd be absolute value of x and then minus
Plus,
3
plus,
or plus
because
3.
we're going up. When you're doing a vertical shift, whatever that is matches the direction you're going. When you're doing this horizontal translation, or horizontal shift, then the direction is opposite of that whole thing.
Okay.
Okay, so what is 2 units up and 5 units to the right?
It would be y equals greater value of x minus 5 and then plus 2.
Good. And the last one is 4 units down and 1 unit left.
So greater value of x plus 4.
No, just because they put it in this order doesn't mean you go in that order. In other words, the 4 units down is a vertical shift. That's got to come at the end after the absolute value.
Plus 1?
Plus 1 is correct. And then minus 4 after the absolute value. In other words, if we'd have started with this, we'd have said that is 1 unit to the left and 4 units down. So don't be confused by the fact that they switched it up on you. They switched it up on you over here also. They put the vertical shift first and the horizontal shift second. they could do it either way. Either way is correct. One isn't necessarily correct over another. Okay. Rewrite this function using absolute value. Well, first of all, just for edification here, let's plot it like we were doing before. Whenever x is greater than or equal to 0, our function is x plus 3. Well, how do I plot x plus 3?
It'd be going up 3.
And then a slope of 1. So that's how I plot that part of it. How do I plot the part that's left of the y-axis? When x is negative, it's minus x plus 3. How do I plot that? What's the y-intercept?
3.
What's the slope?
-1.
Which looks exactly like that, only a straight line instead of a wavy line. But now look at what we're looking at. What is that? How would I plot that using, how would I rewrite this function using absolute value instead of a piecewise function? Notice that I'm looking at the absolute value function here. How can I write that? Y is equal to the absolute value, how? What is that? How does that compare to the parent function?
Wouldn't it be the same just inside absolute value?
No, this has been moved. The absolute y equals absolute value of x looks like this. The vertex is at 0. So this would be the absolute value function shifted how much and which way?
3.
Okay. So it's the absolute value of x plus 3.
Oh.
In other words, this rewrites it in one line what it took this 2 lines to write. This says exactly the same thing. Saying y equals absolute value of x plus 3 says the same thing as these 2 piecewise functions put together.
Oh, okay.
The trick is to see how this compares with the absolute value function. And we can see that it's the same, only it's been shifted up 3 units. All right, let me describe the domain and range of this. Okay, well, let's graph it. That's always the best way to get a handle on domain and range. Help me graph this. I'm going to start on the top line. Whenever x is less than or equal to 2, there's 2, my function is absolute value of x minus 1. So the trick here is to plot the entire thing, x minus 1. Let's plot that. How do I plot that?
Go down 1.
No, it's inside the absolute value markers.
Oh, go right 1.
Okay. So if I was plotting this whole thing, I would go and draw it starting at 1, and I would draw it with 45-degree angle there and a 45-degree angle here, but I have to stop right there. because it's only equal to this when x is less than or equal to 2. So I put a closed dot right there. That's that top part of the function. Now, the bottom part says that y is equal to 1 whenever x is greater than 2. How do I plot y equals 1?
At 1?
It's the horizontal line y equals 1 is what it is. Okay, and that horizontal line looks like this, connecting.
Oh.
Okay, and that point right there is 1 on the y-axis. So there's our function. In other words, to the left of x equal 2, it looks like the absolute value function, absolute value of x minus 1. But to the right of 2, it's a horizontal line. Y is always 1, no matter what x is. Let's talk about the domain and range of that. What's the domain of that?
All real numbers.
What's the range?
Y is greater than or less than, or
Which is it? Look at the graph. Okay. Greater than or what?
Equal to.
And what's the number?
2.
Well, right here, y is 0. Make sure you don't confuse your x and your y-axis, which I see you do every now and then. In other words, when we're looking for possible values of y, I'm focused on this axis here only, not this horizontal axis. When we're talking a range, we're talking the vertical axis only. So if I'm looking at the possible vertical values of y, well, here's one. It can be that. It can be anything in here. It can be all of these values all the way up to infinity. So y is greater than or equal to 0. This minus 2 that you were looking at, or this 2, that's on the x-axis. That's not part of the y-axis. All right. Let's open up this next page here. Although we don't have much time. Wow, what did you take this with? The same camera?
Yeah.
This came out a lot. Somebody was holding the camera steadier on this one. Or do you use a cell phone camera or do you use a scanner?
We use my mom's iPhone.
Ah. iPhones have good resolution on their cameras. Almost got an iPhone just to increase my resolution. My resolution on my camera is 5 megapixels, and iPhones are like 8 or even 12. All right, we got time for one more question here. Determine which of the relations below are functions. Explain how you know and be specific. So, for starters, let's graph it. So the point minus 2, 7 is on there. The point minus 1, 5 is on there. The point 0, 3 is on there. And the point 1, 1 is on there. and the point 2, comma 1 is on there. So if I connect those dots, is that a function?
Yes.
It is. It passes the vertical line test. The fact that there are two y values that are the same given two different x values does not fail the vertical line test. If it was the other way around, it would fail it. In other words, if I had the same y values or two different y values at a given x value, then it would not be a function. And one of these will do that, but we don't have time to get into it tonight. At our next session, we can pick up with number 2 on this page if you like. But number 1 is definitely a function based on those 5 points only. And that, as long as you graph it and connect the dots, you'll be able to tell whether it's a function or not.
Okay.
Okay? All
Okay,
right.
well, thank you.
All right, Marina. Have a good weekend. Sorry you had to
You too.
do this on your Saturday night.
It's okay.
Okay. Bye-bye. Talk to you next
Bye.
time.